Hello, everyone. Thanks for joining this session. I'm Dario from OpenZeppelin, auditor and security researcher. Today we're going to talk about my latest research project, called Contracts Bots Gang. You can check the code base there. You can check it on GitHub under the OpenZeppelin organization. It's open source. You will find it there. For the ones that don't have context about it, it is working with Forta network. And for the ones that don't know Forta network, what it is a network of nodes called scan nodes that execute bots based on new blocks and new transaction happening on chain. So you develop a bot to be triggered for every new block or a new transaction, and it operates what you coded for scanning things. So this project goes about this. So let's take a look at what it does. It's a collection of Forta bots, actually, that tries to detect newly deployed contract on chain, try to deconstruct, decompile them, try to understand some patterns, and then try to run some attacks, well-known bugs, try to break it somehow. So there are 3 steps, basically. You first detect a new contract, you deconstruct it, then you detect some patterns, and then the 3rd step, simulate some attack. And if you succeed in attacking or breaking things, we'll fire a Forta alert. You can subscribe to those alerts, you can react to those alerts, and you can do many things. So let's go step by step. First step, layer 1, the constructor bots. This is in plural because you can actually think about many ways of deconstructing a contract. In the repo, you will find the very first example of one deconstructor bot. But yeah, you can think of many other ways of doing this. The one that you will find in the repo, it's a pretty simple one. It detects newly deployed contracts with transaction to the 0 address with some code in it. That means it is deployed a contract, possibly. We can extract the bytecode out of it. And with the bytecode, we can do the opcodes list, try to understand functions and event signatures. And what it does is also matching those against 4-byte directory. 4-byte directory is the biggest database out there that matches function signatures and event signatures with function definitions with their names. So the very first bot is a little bit small, but an example of an alert of the constructor bot is shown here. You can see it contains several information. It shows the bytecode, the contract address that has been deployed. But more importantly, there are 2 things here: events and functions, and unknown events and unknown functions. Events and functions are the ones that are matched against 4-byte directory, and they are easily recognized to be such function signatures. And then there are the unknown one, and which are categorized there. What we can do with this is then going to the second step, which is use this information to try to understand what the contract is doing, actually. What is hide inside its code. And this is where detectors come into play. The very first detector, again, that you could find in the repo is an interface detector. It basically uses that information with functions and events to understand, oh, this contract is ownable, this contract is initializable, this contract is adhering to some specific interfaces. Now, there are some important things to discuss here. First of all, when this project has been built, it was using a version of the Forta SDK, which is not the latest one. They just updated it this week. But as I said at the beginning, bots reacts to new block and new transaction. But these bots actually relies on alerts from another bot. So there's a little bit of delay added to this sequence because these bots needs to wait for the Forta API to index the data correctly before querying other bots' alerts. Yesterday, they released the new version of the SDK where bots can actually be triggered by other bots' alert directly. So there's an improvement there, and this can be updated to be even more efficient. But take into consideration that what we will find is adding a little bit of delay to take into account the API indexing of data, so that the second step can know about the constructor first. Again, the interface detector bot recognizes all of the OpenZeppelin library contracts, for example, which are pretty much used in many projects, but it also specifies a confidence level, and this is because a function signature is just a 4-byte of the complete signature of the function. It might correspond to several functions. So we must score the confidence level in that sense, saying this might be ownable with some confidence level, because the owner transferred event might be corresponding also, the signature can correspond also to other events. An alert that is typical for this bot is, for example, this one. Again, you got a QR there, and from the QR you can actually go to the bot itself and see all the activities and the logs and the alert that it's firing live. Here you can see it talks about matches. It matches events, it matches functions, and then at the end it outputs an overall confidence and the types of interfaces that the contracts adheres to. So in this specific alert, we have detected a new deployed contract which is not verified on chain yet. We deconstructed on the first step, and now on the second step, we understand that that contract is ownable and initializable with a confidence of 90%. What we can do with this information is now going to the third step, hunter bots. Hunter bots are bots that try to chase down bugs into newly deployed contracts. We're going to talk about the very first example, but you can think of this as a collection of different hunters that can be scanning the blockchain for different type of attacks. Some key features about this third step is that attacks are run in a fork environment, obviously, to avoid unwanted damage to mainnet contracts. It just fork away and then try to simulate some attacks. And they're really automatic in the sense it's a bot continuously firing attacks toward newly deployed contract. We're going to talk about the first example of it, and it goes about a known issue in the UUPS upgradability pattern that we have had in OpenZeppelin a few months ago. The story goes by this. UUPS, it's an upgradability pattern where the logic of the upgrade functionality is stored in the implementation contract itself and not in the proxy. What does it mean is that it works more or less like this. You have a proxy, a typical way of having an upgradability pattern that delegates calls to an implementation. In the specific case of UUPS, you got the upgrade to and the upgrade to and call typical functions of the upgrade logics into the implementation itself. And generally, those are protected by an only admin modifier or something that prevents anyone to call them directly through the proxy. And usually that admin is set to into an initialize function. Remember that when you have upgradability, you don't have constructors into the implementation contracts, you just have an initialize function that is called through the proxy with a delegate call. So the problem was relying on the fact that nobody was actually initializing the implementation. People were only worrying about initializing through the proxy and leaving the implementation logic uninitialized. The problem was that anybody was able to create a malicious contract that was self-destructing into the initialize function, take ownership of the implementation logic, which was left in uninitialized by calling the initialize function, and then upgrade to the implementation to the self-destructing one. The result was that the proxy was completely broken because it was pointing to a non-existing code that was self-destructed. And there are many implementation logic which were left uninitialized. So the solution in the library, in OpenZeppelin library, was to add non-li proxy modifier that was enforcing the fact that the upgrade to logics were called through a delegate call and not directly from the implementation itself. But this example is pretty useful for our purpose, which are hunter bots. In this case, what we need to do is actually detect a newly deployed contract, detect that it adheres to UUPS upgradable interface, and try to break it. So I've done that. We can have. This is like one of the first alerts that I've seen being fired by the bot itself, and this is the minimum result that you can expect. The implementation logic is left uninitialized and can be initialized by anyone. This doesn't mean that you can take ownership of the contract. This doesn't mean that you can upgrade to and self-destruct the things and break everything. But you will be surprised, though, how many implementation logics are left uninitialized. Then we got another alert, a little bit different, by the same bot, that says that contract can be initialized by anyone and ownership can be taken. This means that if you call the implementation logic at the initialize function and then you call for who is the owner, you'll happen to be yourself and you just took ownership of the contract. And this doesn't mean that you can upgrade to and break the proxy. But eventually, you ended up what we are looking for, which is an implementation contract, which is left uninitialized, that if you call it, you take ownership of it, and you can upgrade to a self-destructing contract, breaking the proxy, pointing to it. And remember that UUPS is not having any upgrade logic in the proxy, so there's no way to recover from that, because you completely lose the possibility to upgrade to a new contract. You need to deploy a new proxy and makes things better. One thing, the third step here is the only closed source still part of the project, because it's really sensitive information. We're not sure we want to publish there in the wild, which are the well-known vulnerable contracts. And for this, the bot is public, but the alerts are encrypted. This is like a decrypted version of some of them. That's basically how it works. There is plenty of room to improve things. And for example, one is that the constructor are not catching newly deployed contracts from within a contract. It is only scanning for transaction to the zero address with some code in it, but there are factories of contracts which are deploying other contracts. So an improvement on the constructor can be that. Also detectors, it's not only about interfaces that can be detected, it's also about opcode patterns that lead to possibly reentrancy attacks or external calls and things like that. So there's plenty of possibility to improve the project. The project participated into the latest Gitcoin grant. It received some funding. We are looking for someone that wants to develop this further, so those funds will be designated to people that want to actually build on top of it. Obviously, reach out to me and DM to me if you are interested into participating in that. Yeah, and that's basically it. Most importantly, we are still hiring a lot of people. If you are interested, please reach me out or QR code there, and you can see my socials there. And yeah.
Thank you. So we have a lot of time for questions. Does anybody have any questions?
Just in the example that you showed of being able to initialize a contract, there are like 3 layers to it. So initialize it and then take ownership and then to destroy it. So can you give an example of going from can take ownership to can also destroy it? Would that need to be a function already in the implementation, or is there other ways to do it?
Yeah, sorry. It works like this. It basically comes down to understand how the upgrade to function is coded. It can have an only admin modifier, meaning that you can actually need to be the owner of the contract to call that function, and that's the very first blocker. You need to take ownership of it to be able to call it. But again, the fix in our library was to actually add an only proxy modifier, making sure that the caller was not coming from, the call was not coming within the implementation, but was coming through a delegate call through a proxy. And that's the second blocker. So that's why you see 3 different alerts, because once you detect that a contract is UUPS upgradable, that doesn't mean that you can break it. You can try to break it and see what happens. You can first need to do the initialize thing, then see if you succeeded in taking ownership, and if you did, try to upgrade too and see if you can succeed in doing that. And yeah, the bot is firing all of 3 cases. This case doesn't imply any security concern. It just means that an implementation logic is left uninitialized. But if you know that there are other 2 alerts that can be fired, this means that you didn't succeed in taking ownership of it, and you cannot upgrade to a self-destructing contract.
Hi. So you said that the bot is public, but the data is encrypted. So how does that work? Like, what's the purpose of, or what does it mean, the bot being public, but the data being encrypted?
Bots in the Forta network are public. I mean, you can see all the bots and their activity there. They just fire alerts, which are either plain text, or you can encrypt that and hide the content of the alerts. But the bot themselves are public there. And just to be precise on that, just the third steps of the bots is closed source. The constructor and detectors, if you scan these codes, you will end up into the interface detector bot, and that's plain text. You can see everything there. The only reason is that third bots actually reveal that contracts are vulnerable to something. So if a malicious actor take a look at those alerts, might use them in a non-appropriate way. And that's why also simulations of attacks are run in a fork environment. We don't want to break things just because we are trying to break things.
Just a quick follow-up. So is there any way to subscribe to those alerts currently?
Yeah, sure. If you go to the Forta app, you can subscribe with Slack integration, Discord integration, emails. You can actually build your bots being subscribed to those alerts and do other things. So yeah, there's plenty of integration that you can use.
Thanks.
Do we have more questions? All right. Well, thank you so much.
Thank you.